That's not a typo. That's a real building standing on real ground in Manhattan right now. Stack two statues of Liberty on top of each other. Now shrink the base down to the width of a city bus. That's what they built. Engineers call this a slenderness ratio of 24:1. No tower on Earth has ever been built this thin, this tall, and survived. Why hasn't the wind already snapped it in half? Stay with me, because the answer involves a 90-year-old concert hall nobody was allowed to touch, an 800-ton weight swinging inside the roof right now, and a mistake that almost canceled the entire project before a single floor was poured. This is how you build the impossible. Every skyscraper starts the same way. A company buys land, a clean rectangle, enough room to build whatever they want. In 2005, a developer walked onto 57th Street in Manhattan and looked at a piece of land that should have killed the entire idea before it began. The lot was barely 60 feet wide, squeezed between two older buildings, and directly in front of it sat Steinway Hall, a landmark, concert venue where some of the greatest pianists in history had performed, protected, untouchable. Not one brick of it could be disturbed. Most developers would have walked away. This site broke every rule of what a super tall building needs. Instead, they looked at the impossible strip of land and asked a different question. What if the limitation wasn't the problem? What if it was the design? That single decision turned a real estate obstacle into the world's thinnest skyscraper, and a 15-year engineering war that nobody outside the industry ever heard about. Let's start with the number that makes engineers nervous. Normal super tall buildings sit on a base that's roughly a tenth as wide as the tower is tall. 60 stories up needs a footprint big enough to keep the whole structure planted. The buildable strip measured just under 60 feet across. The design called for a tower over 1,400 feet tall. Do the math, and you get a slenderness ratio no structural engineer had ever attempted on a residential super tall before. At that ratio, wind doesn't just push against a building anymore, it tries to tip it. Picture holding a broomstick upright by the very bottom and blowing on the top. That's the physics this tower was fighting from day one. And the location made it worse. 57th Street runs like a canyon between two rows of buildings. Engineers call this a wind tunnel effect. Gusts get funneled and accelerated as they race between the avenues, hitting anything in their path with more force than open air ever would. The tower wasn't just thin, it was standing directly in the barrel of a wind cannon. So the team had one job before construction even began: figure out how to keep a needle-thin tower anchored to the ground when nature was actively trying to knock it over. The answer started 60 feet below the sidewalk. Here's something most people get backwards. They assume a skyscraper's foundation exists to hold the weight down. On this project, the bigger danger was the opposite. The building was so light relative to its height that high winds could actually try to lift sections of it upward, like tearing a sail off a mast. So engineers designed something almost nobody outside the industry has ever heard of: rock anchors that hold a building down, not up. Crews drilled 200 separate anchors deep into Manhattan schist, the solid bedrock running under most of the island. Each anchor extended nearly 100 feet below street level. Steel tendons were bonded into the rock using epoxy, turning bedrock itself into part of the building's skeleton. It sounds simple on paper. In practice, it nearly broke the schedule. Partway through drilling, one crew hit a hairline fracture in the bedrock. The epoxy wouldn't bond. The anchor was compromised before it even went in. There was no shortcut. Crews sealed the fracture with pressurized grout, let it cure for days, then re-drilled through solid rock a second time. Multiply that delay across 200 anchors, and you start to understand why this foundation alone took years longer than a standard super tall. But when it was finished, the building had something almost no other tower has: 200 points, where Manhattan bedrock itself was physically bolted into the structure above. The wind could push all it wanted. The rock said no. And that solved only half the problem. Because holding the tower down was pointless if the tower itself couldn't resist bending in the middle. Most super talls spread their strength across a wide structural core in the center of the building. This tower didn't have the width to do that. So the engineers built something almost nobody had tried at this scale: 2 massive concrete shear walls running the entire height of the building, working together like the flanges of a giant steel I-beam. Each wall was cast using concrete rated at 14,000 pounds per square inch. For comparison, a typical sidewalk uses concrete rated around 3,000 to 4,000 psi. This mix was nearly 4 times stronger than standard structural concrete, the only formula strong enough to carry 1,000+ feet of building through a footprint this narrow. Threaded through those walls, over 5 million linear feet of steel rebar. Laid end to end, that's enough steel to circle the island of Manhattan roughly 200 times. The walls themselves weren't uniform either. Near the base, where wind forces are strongest, they measured 3 feet thick. By the upper floors, where the load lightens, they tapered down to 16 inches. Every floor was calculated individually. Thicker where the building needed brute strength, thinner where it didn't, shaving weight without sacrificing safety. Pouring concrete at this strength came with its own danger. During one pour, the wooden formwork holding the wet 14,000 psi mix in place began to crack under the pressure. If that panel had blown out, the entire pour would have been ruined, a full stop that could have cost weeks. Crews welded emergency steel tiebacks into place in under 20 minutes, reinforcing the form while the concrete was still wet, and the pour continued without losing a single batch. Then at two critical floors, one roughly a third of the way up, another near the 2/3 mark, engineers added something called an outrigger wall. Its job, physically tie the two separate shear walls into one connected system. Before the outriggers, each wall worked as its own 60-foot wide spine. After them, the two walls acted together as a single structural system nearly 200 feet wide. On paper, that meant the building could now resist wind forces as if it were 3 times wider than it actually was, without adding a single extra foot to the footprint. It's one of the cleverest tricks in modern super-tall engineering, and it still wasn't enough on its own, because strength alone doesn't stop a building from swaying. It just stops it from breaking. Motion was the next battle. Here's a fact that surprises most people. Skyscrapers are supposed to move. Rigid buildings crack. Flexible buildings survive. The real engineering challenge isn't stopping the motion. It's controlling it so residents never notice. On a tower, this slender, uncontrolled motion could become extreme. So engineers installed what's called a tuned mass damper, essentially an enormous pendulum designed to fight the building's own sway. This one weighs roughly 800 tons. It sits near the top of the tower, suspended so it can swing independently of the structure around it. When wind pushes the building one direction, the damper naturally lags behind and swings the opposite way, canceling out a large percentage of the motion before residents ever feel it. During one recorded winter storm, wind gusts hit the tower at nearly 80 miles an hour. Near the top floors, the building swayed roughly 8 inches from its resting position. Without the damper, that motion could have felt closer to double, enough to make furniture creak and stomachs turn. The damper isn't the only trick the design team used against wind either. Look closely at the tower's silhouette and you'll notice something unusual. 2 full floors near the top are left completely open. No glass, no walls, just structural framing exposed to open air. These are mechanical floors, and their emptiness is deliberate. Instead of forcing wind to slam into a solid wall and build pressure, the open floors let gusts pass straight through the building, cutting the force the structure has to resist. It's a strange kind of engineering logic. Sometimes the strongest move isn't resistance, it's getting out of the way. Even with all of that, a building this thin faces problems most towers never think about, problems that only show up once people actually start living inside it. A building's structure can be perfect, and it can still fail its residents in a dozen small, dangerous ways. This tower ran into several, and each one had to be solved before anyone could move in. The doors that wouldn't open. Because the tower acts like a chimney, air pressure builds dramatically at the upper floors during high wind. On one occasion, that pressure pulled a door clean out of a worker's hands. Standard door closers are rated to handle about half the force this building was generating near the top. The fix? Heavier rated hardware combined with a lobby pressurization system that equalizes air pressure throughout the tower. So residents on floor 80 can open a door with one hand, just like someone on floor 5. The pipes that couldn't take the height. Pumping water more than 700 feet straight up generates pressure that standard plumbing simply isn't built for. Early calculations showed the pressure at the pump would run roughly double what typical residential pipe can handle safely. The solution? The entire water system was split into 6 separate pressure zones, each with its own booster pump, so no single section of pipe ever experienced more force than it's rated for. The elevator that almost derailed itself. In a swaying building, elevator rails have to flex with the structure, but flex too much, and a car moving at high speed can actually jump off its track. Engineers measured rail deviation of over 10 millimeters in the tower's most extreme sway conditions. Spring-loaded guide systems were installed to absorb that movement in real time, combined with sensors that monitor rail alignment continuously, catching dangerous deviation before a car ever reaches it. The pool that could break the floor beneath it. High up in the building's amenity levels sits a 75-foot swimming pool. Under the right, or wrong, conditions, water sloshing in that pool can fall into rhythm with the building's own natural sway, amplifying itself into standing waves nearly 3 feet. Tall. If that resonance had gone unchecked, the repeated force could have damaged the structural floor underneath. Engineers installed a perforated steel baffle system inside the pool that breaks up wave formation, cutting that 3-foot slosh down to just a few inches. Every one of these problems shares the same lesson. Building thin and tall doesn't just test the structure, it tests every system inside it, from the plumbing to the elevators to the front door. Every other super tall on this stretch of Manhattan wears the same uniform, floor-to-ceiling glass reflecting the sky back at itself. This tower chose something almost nobody expected: terracotta and bronze. It wasn't a budget decision, it was a design statement. Where glass towers try to vanish by blending into the sky, this one chose to stand apart. Warm, textured, almost architectural jewelry against a skyline of mirrors. But building a terracotta skin for a building, this shape meant nothing off the shelf would work. The tower's 7 setbacks each required a completely unique edge profile. Geometry that had never existed in any terracotta catalog anywhere in the world. 7 brand new extrusion dies had to be custom manufactured just to produce them. Each new die went through roughly 500 sample panels before a single one was approved for the actual building, with a manufacturing tolerance of 0.5 millimeter, tighter than most consumer electronics. The clay itself goes into the kiln gray. Fired at over 1,000 degrees Celsius, it emerges a warm golden color unique to this building's specific mix. Every single panel custom fired for one address in Manhattan. Then came a problem nobody anticipated until the metal actually went up: galvanic corrosion. Wherever bronze panels met aluminum framing, the two dissimilar metals began reacting with each other electrically, and the connections started to fail. The fix was almost embarrassingly simple once discovered. A thin neoprene washer inserted between every single point where bronze touched aluminum, breaking the electrical circuit and stopping the corrosion cold. And because the site had zero room for traditional scaffolding, workers had to hang each terracotta panel using the building's own future window washing track system, installing the skin using infrastructure that wasn't technically meant to exist yet. The result is a building that, from certain angles, nearly vanishes into the skyline. Walk 1 block north, and the 1,100-foot tower disappears behind its neighbors entirely. It's so thin it hides in plain sight. No super tall gets built without moments where the entire project could have gone sideways. This one had at least 3 that engineers still talk about. The lean. Around floor 22, survey crews caught something alarming. The shear wall had drifted nearly a full inch off vertical. On a building this narrow, an error like that compounds with every additional floor poured on top of it. Left uncorrected, it could have thrown off the entire tower's alignment by the time it reached the roof. The fix required 2 precisely calculated construction lifts, nudging the wall a fraction of an inch back towards center each time until the structure was running true again by floor 25. The misaligned embed plate. 2 years before the outrigger walls were installed at floor 38, crews cast steel embed plates into the concrete. Anchor points the future steel truss would eventually bolt onto. When installation day finally came, the bolt holes didn't line up. The embedded shifted 0.6 of an inch sometime in those 2 years. There was no going back to redo 2-year-old concrete. Engineers designed slotted bolt holes to absorb the offset, torqued every connection to nearly 900 foot-pounds, and the misalignment became a permanent accepted part of the structure. Invisible and completely safe. The crane with nowhere to go. Every super tall needs a construction crane taller than the building itself, and eventually that crane has to come down. Standard practice requires enough width on the roof to disassemble it outward. This tower never had that width. When the final floor was poured, the crane was effectively trapped at the top with no conventional way down. The solution? Engineers built a second, smaller crane specifically to dismantle the first one, taking it apart section by section down the building's east face until the final piece finally reached the street. Every one of these near failures shares a pattern. The problem wasn't a lack of skill. It was a site that gave engineers no margin for error and forced creative solutions instead of standard ones every single time. Think about what actually happened here. A team looked at 60 feet of unusable land wedged next to a building they weren't allowed to touch. And instead of walking away, they turned the limitation into the entire design. They didn't fight the constraint. They built around it, through it, on top of it. 200 anchors drilled into fractured bedrock, one red drill at a time until the rock held. A wall poured at 4 times normal strength, reinforced in 20 minutes when it started to crack, without ever stopping the pour. A misaligned embed plate 2 years in the past, solved with slotted holes instead of starting over. A crane with nowhere to go, solved by building a second crane just to take the first one apart. This is what separates a finished skyscraper from an abandoned lot, not the absence of problems. The refusal to let any single problem be the final answer. Every impossible site has one. Every impossible project has one. The difference between the ones that get built and the ones that don't isn't luck. It's what you do the moment the plan breaks, 60 feet wide, 1,428 feet tall, standing right now in the middle of Manhattan, swaying gently in the wind, exactly the way it was engineered to. If this kind of engineering breakdown is something you want more of, subscribe, because this channel exists to pull apart the world's most impossible builds and show you exactly how they actually got made. Drop a comment. Which part of this build surprised you the most? The rock anchors, the damper, or the crane with nowhere to go? And if you learned something from this one, share it with someone who'd geek out over it too. We'll see you in the next build.